Hi, everyone. My name is Mark Russinovich. I'm Chief Technology Officer of Microsoft Azure. And what I'm going to spend with you today is taking a look at Azure, which we consider the world's computer. Where does the term world's computer come from? What does it mean? If we go back a couple years, Satya introduced Microsoft's worldview, Intelligent Cloud, Intelligent Edge, where we're looking beyond just large-scale public cloud data centers to edge computing, the infusion of computing in the world around us. And that includes, of course, our PCs, our phones, but also the embedded computing in buildings, in factories, in cities, in oil wells. What we mean by setting that worldview is that we strive to provide a platform in Azure as the world's computer that is consistent across large-scale public cloud data centers all the way to the smallest of IoT devices as much as possible. That consistency including management, security, identity, monitoring, management, application models, and programming models. Before I talk more about how we're fulfilling that vision of Intelligent Cloud, Intelligent Edge, I'd like to spend a few minutes talking about the ways that Azure differentiates from other cloud providers. We focus on four primary pillars: productivity, trust, hybrid, and intelligence. And with each one of these, we've got differentiated solutions, and the combination makes us truly differentiated. Let's spend just a minute or two on each one of these, where I'm going to highlight examples of how we differentiate. The first being productivity, where more and more productivity for enterprises means open source technologies, whether it's Linux at the foundation or leveraging an open source container orchestrator like Kubernetes. Azure's been focused on supporting open source for many years now, and we've got a portfolio of support for open source, including multiple Linux distributions from Canonical, Red Hat, SUSE, and more, all the way up to higher level frameworks and languages, including some truly unique partnerships with open source community, like our partnership with Red Hat, where we jointly operate Azure Red Hat OpenShift, a Kubernetes service that's built on our own Kubernetes service, Azure Kubernetes Service, or AKS, to Databricks, the company behind Spark, a popular framework for machine learning and data analytics, where we operate a service jointly with them, Microsoft Azure Databricks, where you get the best notebook and Spark experience on any public cloud. But Microsoft's focus on productivity also goes into tooling. Microsoft's been focused on tooling from its very birth as a company. And today, our support for tooling and development extends all the way from the development, from the programmer entering their code in an IDE with Visual Studio Code, the number one IDE on the planet now, fully open source, in fact, the number one most active open source project on the planet, and now adopted by companies that were never even before interested in anything from Microsoft, to Azure DevOps, the world's number one CI/CD platform as a service, which provides you the ability to create build pipelines, integration pipelines, as well as release pipelines, to GitHub, an acquisition we made about a year ago, the place where open source developers collaborate, home to now more than 40 million open source repositories and 44 million active developers. Microsoft making GitHub do more of what it does best, which is open source collaboration. In the last year, we've made a number of enhancements to GitHub, like GitHub Actions, which allows you to create CI/CD workflows on top of your GitHub repositories. If we turn our attention to trust, Microsoft's got a long history of trust and understanding enterprise requirements in security and compliance. Azure demonstrates that with its certification coverage, the most of any public cloud, over 90 certifications spanning global, US government, industry standards, and regional certifications. Microsoft Azure also has the deepest coverage in certifications, where deep means the number of services that meet these certifications. Each of these certifications represents hundreds of security controls. They're a reflection of the fact that we produce evidence that we adhere to them, that give customers and regulators the trust to place their workloads and data in Microsoft Azure. But that focus on security controls extends to the support for keeping your environment and our environment secure. Microsoft follows a first party equals third party principle for security. One of the tools we use to secure infrastructure is Azure Security Center, which we make available to customers. Azure Security Center will look across your Azure resources, notify you of when you've got security gaps, and even make recommendations for how to address them. For many of them, you could address the recommendations right from in the Azure Security Center portal. For example, if you're missing just-in-time access control on your virtual machines, you can simply select the toggle to turn them on to your virtual machines and mitigate them immediately. And what's even better is you, with the guidance of Security Center Secure Score, are guided to prioritize the security enhancements, the gaps that you close, where Secure Score ratings are provided for each mitigation so that you can go after the ones that boost your Secure Score the highest, and that also gives you the ability to track over time how you're improving the security of your service. Now, turning our attention to hybrid, if you take a look at Microsoft's focus on hybrid, it's been there from the very start because we've understood that enterprises, as they move to the cloud, whether it's fast or slow, want a consistent experience with their on-premises resources and their cloud resources. We've got many foundational capabilities that support this hybrid posture, including, for example, Azure Active Directory integration federation, so that with Active Directory on premises, so that you as an enterprise, if you're using Active Directory, can have your users sign on to your local resources and have single sign-on to cloud resources like Azure, Office 365, or thousands of third-party non-Microsoft SaaS and PaaS solutions. We've also got focus on bringing hybrid solutions in integrated systems like Azure Stack Hub, where you get a full Azure from the Azure portal to the Azure control plane, Azure PaaS services, and Azure infrastructure onto as little as 4 servers that you can place within your data center and operate in a fully disconnected mode, to Azure Stack Edge, an edge storage appliance that comes with compute capability for containers and virtual machines, where you can deploy workloads from the public cloud onto it. Azure Arc is our latest enhancement to our hybrid capabilities, where Azure Arc extends Azure's control plane out to resources that are outside of Azure. Our first resources that we support with Azure Arc include virtual machines and servers that you can then manage from Azure, Azure Kubernetes clusters that you can manage from Azure, and SQL analytics clusters that you can also manage from Azure, all as if they were part of your Azure subscription, but operating in your own environment, either hybrid or the edge. And then finally, our IoT solutions address those billions of IoT connected devices with a runtime that connects up into Azure IoT Hub for control and monitoring of your IoT devices, to Azure Sphere, a small device demonstrating first-class security with following the 7 principles of IoT security, providing such value and differentiation that companies like Starbucks are placing them in every one of their stores. Starbucks is using them to connect their coffee machines up to the public cloud so that they can monitor those machines for problems, as well as download new recipes to the coffee makers and monitor the quality of the coffee that they produce. And then finally, intelligence. The intelligence cloud, intelligent edge, is machine learning and AI, and Microsoft's been working in this area for decades now, primarily in support of our Bing search engine, where Bing, when you use Bing, you're looking at images, you're translating text from speech, and a lot of the breakthroughs that we've had in these areas are driven by our Microsoft research labs around the world, including in China. You can see our Chinese Shanghai and Beijing labs are responsible for some of the key breakthroughs that we've made on machine translation, human parity, going from Chinese to English and English to Chinese better than humans can do it. Those innovations flow into our cognitive services, our APIs that serve up these models. For example, you can call an API passing it an image and it will return back to you what objects are in that image. And we go further than just the standard APIs. You can customize most of them. For example, the image API, you can customize with as little as a couple dozen images to understand your own specific images that are relevant to your business. And then you can deploy an instance of that API that your applications can call. More and more, you're seeing us provide you the ability to take those APIs and package them as Docker containers. Once they're packaged as Docker containers, you can take them and run them outside of Azure, in your own data centers or on the edge. One of the examples of why this is so critical for many of our customers is the data needs to stay on the edge, either because there's so much of it that the bandwidth or latency can't tolerate going to the cloud, or privacy concerns make them want to keep the data on the edge. For example, we have retailers that are running machine learning models in stores, so they don't have to send the video up to the cloud, and they can keep their customers' video in those stores and keep it private. And if you're not able to use one of our pre-trained models, you can always turn to our machine learning platforms, which includes Azure Machine Learning, which brings MLOps to machine learning so that you have an enterprise CI/CD type of workflow, you understanding the provenance of the data, understanding what models and versions and tests have been run on those models to make sure that they perform well in production. And we have support for training those models on top of diverse frameworks like PyTorch and TensorFlow, the two leading open source frameworks for machine learning, as well as to deploy those models or train those models on the latest and greatest machine learning hardware, whether that's the latest NVIDIA V100 GPUs in our DC-V3 series, 32 gigabytes, 8 GPUs clustered together with NVLink for massive performance GPU model training, or FPGAs or CPUs. Now that I've gotten a little bit, given you a little flavor for some of the differentiation, let's dive right into what's underneath the hood in Azure. And I'm going to start by talking a little bit about the servers that we deploy or inside of our data centers. Then I'll turn our attention to networking services, physical and software defined, talk about compute layers, Azure Resource Manager, and then I'll conclude with a look at what we're doing in storage. For each one of these, I want to give you a highlight of what those systems look like, and also give you a couple examples of innovations that we either have just released or have coming out in the future. So you can see that the cloud is rapidly evolving, and we're in the deepest wave of innovation that IT has seen ever because of this strong vertical integration from the software all the way down to the hardware. Now, speaking of hardware, the cloud starts with the data center hardware. And let's take a look at some of our data centers. First of all, Azure is a global cloud, truly the world's computer in the sense that we've got more and more regions, 58 and counting, all around the world, multiple in China as we continue to expand. And when we talk about those regions, we talk about them in the context of geographies. Geography being a boundary where customers are happy having their data reside. China being one, for example, geography. Within those geographies, we'll create two regions. One region that will have availability zones, and another one that can serve as a disaster recovery site. In some cases, depending on the size of the regions, we might have all regions, or the geo, all regions with availability zones. But with availability zones, what you get is the ability to tolerate localized failures, failure like a flood in the data center, or even a flood in the local region. A flood that won't impact more than one of those availability zones, where the availability zones are made up of discrete data centers that are separated typically by kilometers. They're close enough, though, that you can replicate data synchronously so that if one availability zone is down, for example, there's a flood or fire in the data center, the other ones continue to operate, and your services then continue to operate. That second region is a region pair, and it serves as a disaster recovery target. If something happens to the primary region, your workload can fail over. Again, looking at meeting the needs of enterprise customers that need high availability as well as disaster recovery. What is exciting to me is really looking beyond the dots on a map and seeing what's underneath the growth of the public cloud. And our Dublin region is one of the sites we call a hero region. It's one designed to grow indefinitely, where you can see how the public cloud demand has led to the rise of data centers. Here's the initial footprint for Azure in Dublin, DB3 and DB4, data centers that were built in 2011, 2012 timeframe. Here you can see DB5 that came along in 2014. That site that you just saw, those 3 data centers, are up there in this larger picture of the Dublin area. And you can see that we've been building out over the last few years here, DB6, DB7, DB8, DB8 coming online in 2017, and we're continuing to build out in Dublin to meet demand for cloud. Here's the future campus works area where you can see lands that's being cleared for additional data center capacity. Truly a hyperscale public cloud region. You may be wondering, what about impact on climate change with all of those servers pumping out carbon? Microsoft's commitment to the environment spans not just our data centers, but the whole company and everything we do. So we're one of the largest purchasers of renewable energy, whether it's water or wind or solar. We've made some of the largest deals in corporate history to procure renewable energy. But we've got a commitment that goes to not just ensuring that we're that we're offsetting our carbon production, but that we're actually completely eliminating it. And not just eliminating it now as we go forward, but also going back in time to pull out from the atmosphere all of the carbon Microsoft's ever put into it. This was a commitment, you can see Satya with Amy and Brad Smith, our president, that we made to go and become by the year 2050 net carbon zero, meaning we'll have pulled out of the atmosphere more carbon than Microsoft's put in since its founding in 1975, not just in terms of data centers, but also our offices, our employee travel, and the suppliers that produce the products that we then put together into data centers or products like Surface Books. All of that will be offset as well. Supported by $1 billion innovation fund to help startups and companies research new ways to pull out carbon from the atmosphere. One of the benefits of Microsoft is Microsoft Research. I mentioned it earlier in the context of machine learning, but we've got many projects with Microsoft Research where they're looking forward for us in the Azure product teams at ideas that may or may not pan out, but we expect to get learnings from. One of them that is really a showcase is Project Natick. Project Natick started a few years ago with the idea that perhaps with a lights out data center operation, we could prolong the lifetime of servers, thereby bringing down the cost of cloud computing. They took a look at this in the context of cylinders, where they place the servers into cylinders and evacuate all of the oxygen and water vapor from them, replacing it with nitrogen gas. And with that, and with lights out operation, meaning no human ever touches those servers, the premise was that these servers would last years longer with fewer failures than traditional data center servers. And with that, we could bring down costs. Further, being on the ocean floor, we could deploy these data centers very quickly. We could have them operate at constant temperature, no need for cooling because they're naturally cooled by the water surrounding them. And we could even power them with ocean currents. So about a year and a half ago, we took 12 racks, about 850 servers, put them in a Natick cylinder, and within 30 days of that cylinder being ready at the factory in Brest, had it turned on in the ocean floor a kilometer off the coast of Scotland in about 100 meters of water. It's been a year and a half, so we already have some insight into how these compare with our land-based data centers. And what we found is incredibly encouraging. The Natick servers have 1/8 the failures and faults of the land-based control servers. The servers taken from the same pool to make it a rigorous scientific experiment. So without a doubt, this lights off operation with nitrogen gas is having a tremendous impact on the reliability of servers. That combined with the agility we get out of deploying these containers and having all of this space basically to deploy them, 50% of the world's populations within just a few kilometers of the shoreline, we're proceeding on to the next phase, Natick V2, where we're going to take 12 of these, put them on a gantry that feeds power and networking to all of them, and drop that to the ocean floor. And with lights out operation, if one of the cylinders starts to degrade, the servers start to fail in it, To replace that capacity, we simply pull up that cylinder and replace it with a fresh one. So truly potential revolutionizing the way that data centers are operated, both on underwater as well as on land. Now let's take a look at our servers. Now for that, I want to take you a walk down memory lane back to the servers we were using in 2010, which is when I joined Azure. They were our Gen 2 servers. Back then, the cloud was considered commodity and scale out, and you can see that they had 32 gigabytes of RAM, they had no SSD, 1 gigabit of networking switch. But what we found out quickly as customers started to migrate enterprise workloads is that they wanted large scale-up servers as well. SAP, HANA, other in-memory databases require huge amounts of memory. And so we started deploying large servers, starting with our Godzilla server, our G-series virtual machine you might be familiar with. These servers had 512 gigabytes of RAM. They were considered monsters at the time. That wasn't big enough, so a few years ago we introduced Beast, going to 4 terabytes of RAM to support even larger SAP HANA migrations to public cloud. You can see that the Gen 6 servers that we're deploying in our mainstream fleet today, they're larger than the Godzilla servers were 4 or 5 years ago. We are now deploying both Intel and AMD servers so that we've got the best of both companies' technologies available to you. And it turns out that SAP HANA workloads are getting bigger and bigger, and our enterprise customers want to move those to public cloud, and so we've had to introduce bigger servers than Beast. Beast V2, or son of a beast. This has 8 sockets with 28 cores per socket, 12 terabytes of RAM in it. And we expect to even be bringing and building larger servers because our customers are creating ever yet bigger SAP workload deployments that they want to bring to the public cloud. Azure being the number one place where enterprise runs SAP in public cloud. And I don't want to leave out Sphere. I mentioned it earlier. Here's our Intel Gen 7 and AMD Gen 7s that we'll be deploying in the next few months. You can see the latest and greatest technologies from Intel and AMD. But Sphere, with just 64 kilobytes of RAM, wouldn't be visible in this chart without the help of this giant magnifier. And you can see Azure spans, as part of Intelligent Cloud, Intelligent Edge, all the way from tiny Sphere devices on the edge to massive Beast V2s in the public cloud. When it comes to innovation in servers, one of the places we're looking is to meet this trend of CPUs and GPUs, which are drawing ever increasing amounts of energy. Are those GPUs from NVIDIA, the latest ones, the Volta V100s, that come in appliances called DGX2s, 8 together, combined draw 10 kilowatts of power. To put that in context, a data center rack is provisioned for about 14 kilowatts of power. So that means we could, given current cooling, only put one DGX V2 appliance in a rack, occupying all of that space for just those 8 GPUs. This is pushing us to look at more efficient ways to cool our data centers so we can pack them more densely and make better use of the space. Here's our air-cooled servers. We're looking at microchannel cold plates, which is the liquid cooling that you might even have in your home gaming systems, liquid cooling that is going through plates that are attached to the GPUs and CPUs, to single-phase immersion, where we put the whole motherboard or main board inside of a liquid, to two-phase immersion, where it's a liquid that has a very low boiling points for extremely efficient cooling. These are technologies that we're working on and we expect to see in production in the not too distant future. Innovations that for an enterprise would be very difficult to go fund or deploy, but we're doing it in conjunction with the design of our servers, and so we can very quickly bring these technologies out and make them available. Another example is where we work closely with our partners, like Micron in this case, to bring you the latest and greatest technologies and even influence the way that those technologies are created to suit public cloud. In the case of Micron, we've developed a Scudi type storage device based off of 3D XPoint, a truly revolutionary storage technology that is like flash because it's durable, but also like DRAM because it's extremely low latency. And we worked with Micron to create devices that have the ability to partition the devices so that we can give pieces of them to different customers and have them get a great reliable, performant, consistent experience on them. I'm going to show you a quick demo of Scudi in action. On the left, you can see a standard SSD deployment, a virtual machine with an SSD attached to it. On the right, one that has a Scudi device attached to it. And what I'm going to do is launch here a benchmark on each one of them that drives as much data to those drives as possible, as they will support. You can see this SSD supporting about 2 gigabytes per second, the Scudi device over 9 gigabytes per second. But how does that translate into real-world performance? For that, I'm going to run a SQL query, one from the TPCH benchmark suite, on each one of those systems. It's a 500 gigabyte database, and when I execute the query on the SSD, you can see on the left side, the disk transfer seconds per transfer comes to about 20 milliseconds per I/O. And the query here, it just completed, took about 18 seconds. Now let's compare that with what we see on the Scudi device. So opening that same query now on the Scudi device, 500 gigabytes, and running it, we've got to pay close attention because it's completed. And the disk seek time, the seconds per transfer, is about 2 milliseconds. So about 1/10 the latency of what we saw on the SSD. And the total query, it took just 4 seconds as opposed to the 18 seconds we saw. A dramatic difference. Just one of the innovations we're working on with hardware partners like Micron. Now let's take a look at Azure networking. And networking spans everything from the physical WAN to all of the software-defined services like DDoS protection, VPN, virtual networks, firewalls, out to connections with the outside world, whether that's the edge or enterprise networks through ExpressRoute and Express Route Direct, which support up to 100 gigabits of bandwidth that goes directly from an enterprise network into Azure's network. And that network spans the world. 130,000 kilometers of cabling, 160 edge sites, 500 network partners and growing. A network that we control our own from end to end. So when traffic enters our network and goes out across the world to another region, it stays completely on our dark fiber. One of the innovations we're working on in the networking is making containers. You might be familiar with Docker containers. Traditionally, containers have been implemented with what are called overlay networks that have nothing to do with the underlying network of the cloud provider. And that means that you're missing all of the cloud provider's features like the routes, like firewall rules that you can apply using cloud APIs. With Swift, we're bringing the underlay Azure SDN, Azure Software Defined Networking, to containers. And the way that works is by an agent that delegates a customer's network into the container orchestrator, like Kubernetes. So as the containers get deployed, they can sit in the customer's network, even though those virtual machines that the containers are in happen to be on top of the Kubernetes network. Let me show you an example of that in action. So first, I've got 2 virtual machines. I've got them inside of an infrastructure virtual network. Here I'm looking at the address space for this virtual network. You can see it's a 10 dot space, and when we see a 10 dot address, it's the virtual machine itself. One's at 10.4, and the other one's at 10.5. Now their customer network, where the containers are going to run, that one has a different address space. Its range is 172.20. So when you see a 172 address, that is the container. Those containers are going to run in those virtual machines. And we've got 2 flavors of those containers. One that's running in the virtual machine that has accelerated network or high bandwidth network, and one that's not. So you'll be able to see that they are, here we're launching one container in one virtual machine, the 172 address, and another container in the others. And these are sender-receiver pairs of containers in each of these virtual machines. They'll just send data to each other as fast as they can. One accelerated on the accelerator virtual machine, the other pair non-accelerated. And you'll be able to quickly see as they start to report their results, which is which, because the accelerated one is going to be driving much higher bandwidth than the other one. You can see this is about 2 to 3 gigabits per second, and that is not anywhere close to the 20 gigabits per second that we see on the accelerated network. And you can see that both of these are running inside of different virtual machines, delegated subnets, and so this is really giving first-class networking capability to containers. Now let's take a look inside of compute, and where compute starts with Azure is in Azure's control plane. Azure's control plane is called Azure Resource Manager, or ARM. And ARM is a universal control plane. Every Azure service plugs in. ARM provides every Azure service, whether it's Azure Kubernetes Service or Azure Key Vault or SQL, with common capabilities, with the ability to model them in templates, with monitoring for them, with role-based access control, and with Azure Policy. Azure Resource Manager provides consistent capabilities across all of them. And that's where Arc comes into play, is extending those consistent capabilities out to resources that are outside of Azure. Now, another part of compute is, of course, related to running compute workloads. And we're developing a next-generation compute fabric called Atlas that is highly optimized for running containers, because today, while most enterprises are running on virtual machines, in the future, the world is going to containers and container orchestrators. We've got a common container orchestrating platform, Atlas, that underlies all of our container-based services, whether that's AKS, Azure Kubernetes Service, ACI, Azure Container Instances, Azure Functions. All of those are moving to run on top of Atlas, which is based off of our own internal container orchestrator service fabric. We're also making innovations in making containers operate better, not just in networking, but also have higher performance. One of the challenges with large containers is that if you take a look inside of a container, they're made up of images that are layered on top of each other. And before you can launch or start the code that's in a container, you need to load all those images. And if for a large container, that can take a long time. With something called Project Teleport, we're making it so that those containers can start in a fraction of the time, because instead of loading all of the containers, we just simply mount those images on file shares. And once they're mounted as file shares, we can start executing without having to pull all the data across from the servers. They get faulted in on demand. And you can see dramatic differences. A dedicated virtual machine launching a 5 gigabyte container takes about 412 seconds to read in that entire 5 gigabytes. If you take a look at Azure Container Instances or serverless container offering, it takes a little longer, because that's a multi-tenant resource aimed at high-density containers. Now with Project Teleport, that 412 seconds turns into 7.6. We're also looking at the next generation of cloud-native platforms. So writing a distributed application is extremely hard. There's so many things you got to worry about. Different SDKs to integrate with, for PubSub, for state management, for service discovery, as well as having to deal with all of the issues with how do you route, how do you do retries and backoffs. All of that is work that the enterprise developers would rather just have the platform take care of, so they can focus on solving their problem. But today, the challenges in delivering something to address their needs range from the fact that they're being asked to develop these resilient services, microservice-based apps, but they write them in many languages: Go, Rust, Python, JavaScript, Java, C#. And when they're writing an application, they want to leverage a lot of existing code, not just write it all from scratch. They're also, when you take a look at what enterprise developers have really resonated with, it's actor models and functions as a service. Functions being event-driven, serverless pieces of code. where the platform takes care of all of those distributed systems kinds of problems about failures and retries and scaling for the developer. So we've introduced and we're working on the next generation cloud native programming model platform called Dapper for Distributed Application Runtime that is aimed at solving the needs of enterprise developers. I'm going to show you a quick demo of Dapper in action. I don't have much time to get into it, but this demo really highlights just how powerful it is. The idea here is we're writing a distributed app calculator, one where every one of the calculator operations, plus minus division, is represented as a different microservice. First thing we do is take advantage of Dapper's sidecar, which is represented as an HTTP interface. We can talk to Dapper through that interface, and we can do things like tell Dapper to save state, like what is the current state of the calculator. We can just call an API there on a local endpoint and save the state. But you can see we can also call Dapper microservices using these different Dapper invocations. Subtract, just by calling the subtract microservice through an HTTP request. And for each one of those microservices, like here's the addition written in Go, it's simply a web server that's integrated with Dapper. So Dapper will call the Go web server, passing it the request. It simply adds the inputs together. The subtractor, same thing. Dapper will call it, and with the subtract. Here we see a multiplier written in Python. You get the idea. This one's got a Flask web server, and that's the entire code for the microservice. Here you see a divider written in JavaScript. And that front end was simply calling these Dapper microservices. Dapper worries about where they are because these are going to be deployed on Kubernetes. So they'll be in containers on different servers. Dapper worries about getting the request from the front end to these different microservices. So speaking of Kubernetes, here I'm going to get pods, and you can see I've deployed the application, and we can see the Kubernetes pods for the adder, for the front end, for the divider, for the modulo function, for the multiplier. The modulo is written in Fortran, just to show you that any language can integrate with Dapper. That is the entire app you're looking at. That's just a few hundred lines of code in 5 different languages. And what I'm going to do is now open up that calculator by going to its URL. I'm going to show you on the right side, you can see the logging of the Dapper calls to save state, to perform those different operations like add, subtract, multiply. I'm performing a bunch of operations. You can see I'm going to leave here the calculator. There's the state is 1. That's the current state. I'm going to refresh the web page here, and you're going to, in a second, and you can see that it remembers that its state was 1 by calling into Dapper and saying, what was my state? So externalize the state to Redis cache in this case, or Cosmos DB, or whatever. You can see we get, because we're on Dapper, we automatically get tracing. So you can see the invocations from the front ends to the different microservices, including how long they took. This is application insights built right into Azure. The data was collected by Dapper and forwarded. So with no work on the developer's part, we get full insight into the way the application ran. And then we can also look at the list of operations discretely. So Dapper really represents a breakthrough, we think, in the way enterprise developers can write distributed microservice-based applications. Now finally, I want to take a look at storage. And storage includes lots of different services from HDFS to NFS to SMB, all built on top of a common storage infrastructure that supports all different tiers of storage, from hot, that would be sitting inside of SSDs, to cool storage on hard disks, to archive storage. I mentioned our work with Microsoft Research, and a few years ago we started looking at archival storage, how we could make that cheaper. And the way that we're doing that is with storing data in glass. Glass, you might be wondering, what's the benefit of that? Well, if we can store data in glass, we can store it in 3D. We can store it extremely efficiently in what are called voxels, which store, when we write those voxels with femtosecond lasers, different bits of information using retardance and polarization angle. Each one of those voxels can store multiple bits. And by etching all this information in glass, we get the benefits of glass which is just extremely durable. You never have to rewrite it. It doesn't degrade. You can do things like boil it. You can degauss it. You can scrape it with steel wool even. Because the data is in the glass, not on the surface of the glass, like it would be for a Blu-ray disc or CD. You can even microwave it. And finally, you can bake it at high temperatures. Glass is extremely durable. It's also extremely cheap. It lasts for millions of years. And here you can see that we were able to read back the data that we'd written into that piece of glass that went through that extreme torture test. And we've partnered with Warner Brothers to store the movie Superman in a piece of glass and successfully read it back, a big milestone we announced at Ignite. This was going to transform the way the media industry stores their content, which is their lifeblood. Up to now, they've been storing it in analog form. Now they can keep it in digital form. They never have to reread it to like they would with the film that they were storing. And film decomposes if it's exposed to any of those tests that we exposed the glass to would be degraded. But here, the Superman movie is going to be safe for thousands or millions of years, so that Warner Brothers can go back and re-release it, reuse all that content. Again, just one of the many types of innovative projects that we have in Azure and with Microsoft Research to advance the cloud and make it more powerful for you. So that brings me to the conclusion of the talk. I hope you found this interesting. I hope it gave you some insight into Azure's differentiation, hybrid, trusted, productive, intelligent, as well as a look underneath the hood at our data center, servers, compute, network, and storage, including some of the innovations that we've been working on. Thanks very much, and I hope to see you on Azure.